So let's look at light and how light diffracts. We know that light can bend when it travels through media, like water or glass, and it will travel faster when it goes through other mediums or media like air. But how does this work? How can light slow down and speed up through different media? Well, from the wave-particle duality principle, we know that light can be a wave. So let's draw this out. And there's a barrier between air and water. And for this example, let's use a green light wave. So in air, the light wave looks like this, and in water, it'll look like this. And when it goes back to air, it'll look exactly the same thing. And let's say the period for this wave is 1 second. But in water, the crests are bunched together, even though the period for each wavelength is still 1 second. So in this example, it took the green light 1 second to travel through air, but 2 seconds to travel through water, and again 1 second to travel through air when it comes back out from water. So if you notice, the light that we start with is green. The light that goes through water is also green, and the light that comes back out is still green. And why? Because the frequency does not change. It is constant. This is why the light stays the exact same color. Now there's still one more point to discuss, the speed of light. If light is always traveling at 3.00 times 10 to the power 8 meters per second, then how is it possible for light to speed up and slow down? Again, applying the wave-particle duality principle, we can say that light can be a particle. So let's look at an example. So this is our light source, and it can go through air, and it can go through, say, glass. Or this can also be water or some other transparent material that light can go through. So these are air molecules. These are the glass molecules, or anything that makes up glass, or the transparent object that you choose. So when light travels through this air, it'll just go through like this. But when it goes through glass, it has to go past these molecules. These molecules, they're barriers before they can go up through here. So this is why if the light travels through glass, it travels at a, quote, slower speed. But from one molecule to another molecule, this distance here, light travels at the speed of 3.00 times 10 to the power 8 meters per second. C. For example, say there is a really famous person who is visiting at UBC, and you're a big fan of this person. So this person is here. And there's you. And there's also a bunch of other people because this person is really famous. So between you and this very famous person, there's a crowd of people, and just exactly like the light source that we showed earlier, you can't just go across and go through all these people. You have to go around all of these people before you can get to this person to get their autograph. Again, maybe when you're traveling these people, you're going at your fastest speed. Your fastest speed being, say, 1 meter per second. If all these people weren't here, and you could still go exactly through to this person, you would still travel at your fastest speed, 1 meters per second. Exactly like how light travels through glass. Except when there are people here, you can't take the shortcut, which is directly to this person. But when there are no people, no barriers, no glass molecules, you can go exactly straight through to your destination, your source.